Crosstalk problems on the PCB can be easily located and fixed using HyperLynx. After exporting your design from PCB layout, run simulations in batch mode and/or interactive mode to identify potential crosstalk issues. BoardSim's coupling region walker enables you to pinpoint exactly where the most coupled regions of a net are. Also export the net to LineSim to edit the coupled sections to eliminate the crosstalk issue, and then determine the changes that need to be made to the layout. So let's take a quick look at identifying and resolving PCB crosstalk issues. You can analyze all of the nets on the board using batch analysis. You can also analyze individual nets interactively. I'll focus on a specific region of the board with densely packed traces and select an individual net for crosstalk analysis and enable crosstalk simulation. All nets coupled to the selected net also become selected and will be included in the simulation. Coupled nets are determined by the coupling thresholds, which can be set up to use expected coupling voltages or just simple geometrical checks. After running the crosstalk simulation on the selected net, it is clear that there is a significant amount of crosstalk present, and zooming into the far end of the crosstalk waveform, you can see that the level is sitting at around 300 mV. The coupling region walker can now be used to determine which areas of the layout are causing the most crosstalk. And the strongest coupling region is in the main section with only 4 mils of spacing between traces for a distance of about 1.2 inches. There are also some other shorter sections with about 200 mils and 100 mils of coupling, and some other even shorter sections. If I were to change the coupling on these 3 main sections, it would be a significant reduction in the crosstalk. I'll now export to LineSim to analyse those effects to determine the optimum trace clearances. The exported schematic has a large number of different coupled cross sections, but if I zoom in on the victim trace, it's relatively easy to find specific segments of the net that warrants further investigation. In this case there's the 109mm section, the long 1.294 inch section, and the 214mm section. If I select one of the sections, I can review its cross section, and the field solver helps visualize the E field and H field coupling between the traces, otherwise known as capacitive and inductive coupling. The sweep manager can be used to set up different trace spacings to determine their effect on reducing the amount of crosstalk present. If I select one of the spacings, I can then set a range. So let's look at the effect of going from the existing 4mm spacing up to a 20mm spacing in increments of 4 mils. I can then copy that range to all other trace spacings so that they can all be changed simultaneously in the simulation. Those spacing ranges can be copied to other cross sections as well. That way, I can select all of the cross sections that I think are significant and sweep their spacings to find the optimum level for minimal crosstalk. Once I have everything set up, I can run the sweep simulations. The simulations run fairly quickly, and we can see the results overlaying on one another as they run. Once complete, I can zoom in on the crosstalk waveforms and look at the results of the different spacings. The original case with the 4mm spacing shows about 300 mV of crosstalk. If I double that spacing to 8 mils for those sections, notice that the crosstalk would be reduced to around 150 mV. And a 12mm spacing or greater reduces the crosstalk level below 100 mV. So if there is space in the PCB layout, 16 mils is probably the ideal trace separation, as it would reduce the crosstalk to below 50 mV. Now I know what to aim for the target value for spacing in the layout, and make those changes accordingly. You've now seen how easy it is to eliminate crosstalk issues from your PCB design, and how HyperLynx can give you the confidence that your design will be done right the first time, saving you valuable time and money in your design cycle.